In the chapter Ray Optics and Optical Instrument, we are going to discuss about various phenomena related to light. We know that a beam of light is represented using rays, and when a light ray is obliquely incident at the interface of two media, then the direction of propagation of light ray changes as the ray enters to the other medium, and this phenomenon is known as refraction of light. You might have already learned the phenomenon called refraction of light, and we know that there are two laws of refraction, and the first law states that the incident ray, the refracted ray and the normal to the interface at the point of incidence all lie in the same plane, and the ratio of sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media, and this second law is known as Snell's law. So when the light ray is obliquely incident at the interface of two media, it is partly reflected and partly refracted. A part of that incident ray gets refracted and enters to the other medium, whereas a part of the incident ray reflects back to the same medium. And the perpendicular drawn at the point of incidence is known as normal. So this is the phenomenon of refraction. And as we told, the second law is also known as Snell's law, and according to Snell's law, sin I by sin r is a constant, and that constant is known as the refractive index of medium 2 with respect to medium 1. So the angle made by the incident ray with the normal in the first medium is the angle of incidence, and after refraction the refracted ray makes an angle with the normal in the second medium, and that is known as angle of refraction. And the ratio of sine of these two, that is angle of incidence and angle of refraction, gives the refractive index of second medium with respect to first medium. So N21, which is the refractive index of second medium with respect to first medium, is given by sin I by sin r. Now, based on the speed of light in a medium with respect to the other medium, we can call the medium as optically denser medium or optically rarer medium. Let us see how we can define optically denser and optically rarer medium. If the light ray travels slowly in a particular medium with respect to the other, then that medium is known as optically, and when light ray travels faster in a particular medium when compared to the other, then the medium is known as optically rarer medium. So based on the speed of light, we are defining the medium to be optically denser or optically rarer. And we have to keep in mind that this density that we are defining here has nothing to do with the density related to mass. The mass density that we define by the ratio of mass by volume has nothing to do with the density that is optically defined here. During refraction, the light ray entering from one medium to other bends and changes its path. So when light enters from optically rarer medium to optically denser medium, the light ray bends towards the normal, whereas when light ray enters from denser medium to a rarer medium, it bends away from the normal. So as we told, from rarer to denser, the light ray bends towards the normal. Therefore, here we can see that the angle of incidence will be greater than the angle of refraction, because the light ray is bending towards the normal means the angle of refraction will be less than the angle of incidence, and therefore we can say that sin I by sin r will be greater than 1. That is, the refractive index of second medium with respect to first will be greater than 1. So this is an important conclusion that we obtain by analyzing the refraction phenomenon. The refractive index of second medium with respect to first will be greater than 1 means the first medium will be rarer and second medium will be denser. Whereas in the opposite case, that is when light ray enters from denser medium to a rarer medium, the light ray deviates away from the normal after refraction. That is, the angle of incidence will be less than angle of refraction. Therefore, sin I by sin r will give a value which is less than 1. That is, the refractive index of second medium with respect to first will be less than 1. When refractive index of second medium with respect to first medium is less than 1, we can obtain a conclusion that the second medium is rarer and the first medium is denser. So, some conclusions that we obtain on analyzing the refractive index for a given pair of media. The first one is that if refractive index is greater than 1, then light travels from rarer medium to denser medium, and refractive index is less than 1, then light travels from denser medium to rarer medium. And if we are having 3 media, that is light travels from medium 1 to medium 2 and then to medium 3, and if we know the refractive indices of each pair of these media, then we can write the relation as N32, that is refractive index of third with respect to second is equal to N31 into N12. As you can see, the subscripts are having particular pattern, that is N32 can be equated to N31 into N12. So, this is an important relation that we obtain when we are having more than 2 media for refraction. Another effect of refraction is that when we observe an object at the bottom of a water source, we can see that the object appears to be raised from its actual position. We all might have come across with this experience in a pond or in a river. When we observe the stones under water or the fish in water, we can see that the stone or the fish appears to be displaced from their actual position. What happens here is the refraction of light. That is, imagine the observer is watching an object under the water. So, the light ray from the object through water enters the air. So, from denser to rarer medium, the light ray enters. So, light ray enters from denser medium to a rarer medium. So, the light ray deviates away from the normal. So, due to this deviated light ray that reaches our eyes, the object appears to be displaced and raised than its actual position. So, if we extend the light ray that reaches our eye, we can see that the object appears to be displaced, and this apparent depth of the object depends on the refractive index of the media, that is refractive index of water. So, we can relate the apparent depth and the actual depth with the refractive index of the media, and the relation is apparent depth is actual depth divided by the refractive index of water. So, H prime, which is the apparent depth, is equal to H, the actual depth, divided by refractive index of water. So, this is another important observation that we obtain due to the phenomenon of refraction. Also, the twinkling effect of stars is due to the repeated refraction through different layers of atmosphere, which vary in their optical density from one another. That is, as we know, our atmosphere around the earth is having different layers like stratosphere, troposphere and so on, and all the layers are different in their optical density, and therefore when light enters through the atmosphere from a star, the light undergoes repeated refraction as it enters from one layer to the other and so on, and due to that the stars appear to be displaced for each refraction, and that causes the twinkling effect of stars. So, as light enters from a star through the atmosphere to an observer, the light as passes through the atmosphere, different layers of the atmosphere, it undergoes repeated refraction through each layer, and due to that the star appears to be displaced repeatedly as we observe the star, and that causes the twinkling effect of stars. Now, another important impact of refraction is that the sun is visible a little before than the actual sunrise. So, even before the sun rises from the horizon, the light ray from the sun reaches on our eye, and due to that light ray we see the sun with an apparent shift. That is, the sun appears a little before to us than its actual sunrise. So these are some of the important impacts of the phenomenon called refraction. Now another important phenomenon of light is the total internal reflection. So as we told, when light travels from one medium to other, a part of incident ray gets reflected back and also other part is refracted. For total internal reflection to occur, our light ray must always travel from denser medium to a rarer medium. So when light travels from a denser medium to a rarer medium, at the interface it is partly reflected back into the same medium and partly refracted to the second medium. So this reflection is called internal reflection. As we told, the incident ray, when it travels from a denser medium to a rarer medium, the incident ray is partly refracted to the other medium, and since it is traveling from denser medium to a rarer medium, the refracted ray moves away from the normal and other part of the incident ray is reflected back to the same medium. Now we know that as the angle of incidence is increased, the angle of refraction also increases. That is, if we further increase the angle of incidence, the refracted ray gets further deviated from the normal. So we are increasing the angle of incidence, and we can see that as angle of incidence is increased, the refracted ray further deviates and angle of refraction also increases. Now on increasing the angle of incidence again and again, for a particular value of angle of incidence, we obtain the refracted ray that is gazing through the interface. That is, the angle of refraction here is 90 degree. So for a particular value of angle of incidence, we obtain an angle of refraction to be 90 degree, and this angle of incidence for which we obtain the angle of refraction as 90 degree is called the critical angle. So the angle of incidence for which we obtain the angle of refraction to be 90 degree is called the critical angle. So as we told, when the angle of incidence is the critical angle, then the angle of refraction will be 90 degree. Therefore, here the refractive index N21, which is sin I by sin R, is sin IC, where IC is the critical angle, by sin 90, because the angle of refraction is 90 degree. Thus the refractive index N21 is sin IC. So as our angle of incidence is the critical angle, the refractive index N21 is equal to sin IC, and from which we can write N12 is equal to 1 by sin IC. Now what happens when the angle of incidence is further increased, that is, angle of incidence is greater than the critical angle? During this we obtain the phenomenon called total internal reflection. The light ray incidenting at the interface gets reflected back completely, and this phenomenon is called total internal reflection. So from the study we obtain the conditions for total internal reflection, as the light ray should travel from denser medium to a rarer medium, and the angle of incidence should be greater than the critical angle.